Hey there, it's Shannon Myers coming at you live again from San Diego, California. I hope you are enjoying your day. Today we'll be looking at direct proof and counterexample part 2, rational numbers. So we will continue learning techniques of proof, and this will be related to rational numbers. So fasten your seatbelts and enjoy the show. Here we go. A real number R is rational if and only if it can be expressed as a quotient of two integers with a non-zero denominator. A real number that is not rational is irrational. More formally, if R is a real number, then R is rational if and only if there exist integers A and B such that R is equal to A over B and B is non-zero. So first example, determine whether the following numbers are rational. Remember, if you have a negative outside the fraction bar of a ratio, you can either be attached to the numerator or the denominator. Now notice that in both cases we have a quotient of two integers, and so we would say yes for this one. What about the number 21? Awesome. I'm sure you guys were thinking that this could be written as 21 over 1, and both 21 and 1 are integers, so we fit our definition for a rational number. So that's a yes as well. And then for number 3, what about that number E? Well, you've probably examined this a bit in pre-calculus. At our school, we only require pre-calculus as a prerequisite for discrete math. So just in case you're not familiar with it, this is actually a limit. So it would be the limit as x approaches infinity of the quantity 1 plus 1 over x raised to the x. So I won't do that whole limit for you, but you'll be seeing that in calculus when you take that, if you have not already. So it ends up where it's not rational. It ends up being this limit where it approaches this value that we often, round to like 2.712-ish. But it's not something that can be made into a fraction of integer over integer form. All right, what about 0.432? I mean, if we spoke this properly, what would we say? We'd say 432 thousandths. Very good. And so this indeed fits the definition because we can write this as a quotient of two integers. So this is a yes. Sorry, this one was a no. And then what about a repeating decimal? I mean, it turns out, and you'll learn a different technique when you're in calculus too. You may have already learned it in pre-calc, but one easy way to find out what the fraction is that represents this repeating decimal is to basically, if you let x equal to your repeating decimal, so this is 0.432, 432, etc. Right? And then how would I get rid of one of the repeating parts? Not rid of it exactly, but how many digits are repeating? Very good. 3 digits are repeating. So if I multiplied x by 1,000, wouldn't I then get 432.432, because it keeps repeating, right? Well, what if I subtract? What would I get on the left side? Great, 999 x's. And then that would equal to 432.0000000, etc. It would go on and on like that, right? And then isolating x, we would get 432 999ths, which is of integer over integer form, right? So this actually is a rational number. Pretty awesome, huh? You can also find these using geometric series. And that's how you would do this in calculus too. All right, so if m and n are integers and neither m nor n is 0, what about m plus n over the product m times n? What do you think? Well, if you look at the numerator, what are you doing? You're adding two integers, right? And they're non-zero integers. And so what would we get? We would either get some sort of integer, and it'd be fine to get 0 in the numerator, right? They could be opposites of each other, it doesn't matter. But they are both given to be integers. Now, there's something that you might not remember about the zero product property. In fact, let's go ahead and sneak down here. For the zero product property, if neither of two real numbers is 0, then their product is also not 0. So here, by closure, so remember when you add two integers, you get an integer, right? So that sum belongs to the set of integers. And the product also belongs to the set of integers. And furthermore, m times n is not equal to 0 by the zero product property. So m plus n over m times n is rational. Okay? All right, so we'll give this one a yes. So now let's take a look at some of these theorems. Now, what we're going to do is we'll be proving a lot of these theorems in the next couple sections, and a lot of them are already in your book, but I thought it was important to also prove them for you. So this first theorem we're coming across, 4.2.1, is every integer is a rational number. So let's get our proof toolbox out here. And so first of all, you want to make sure that you are writing proof so people know you are doing a proof. And here, every integer is a rational number. Well, what do we need? What do we need? And sometimes this is so easy, it's hard. We actually did sort of an example here. Wasn't 21 an integer for example 1 part 2? This one right here. And we said yes, because you can always do 21 over 1, and that is of the form integer over integer form. So here, if we let n be any rational number, let n be any integer, can be any integer. That was about me being about to assume what I was going to prove, right? Classic error. Okay, so let n be any integer, right? So the evil plan is we have to show that no matter what happens, that this n will be rational as well. Okay, so n is equal to n over 1, correct? Even when n is 0. Which is rational, and that's by definition, right? By that definition of rational numbers. So, therefore, every integer is rational. And we're all done. Cool so far? All right. Next theorem is theorem 4.2.2. And this theorem states that the sum of any two rational numbers is rational. Now, okay, it's often good to restate something into an if-then format, right? So that you can prove it. So let's just take a look at what's the premise and what's the conclusion in this statement. So the sum of any two rational numbers is rational. So what do you think this is saying? Couldn't this also be saying if R and S are rational, then R plus S is rational. Does that make sense? I basically named them, right? So let's kind of go with that. So I'm going to start my proof. And I'm going to say, suppose R and S are rational numbers. Well, since we've got rational numbers, there's going to exist integers A, B, C, and D with B not equal to 0 and D not equal to 0, such that R equals A over B and S equals, good, C over D. Well, what do we have then? I mean, we got to add them, right? R plus S. Well, when we add those up, what do we get? Awesome. We're going to get A over B plus C over D, and that's just by good substitution. Alrighty. Well, what will this be in term? If I get common denominators, wouldn't it be perfect? A times D over B times D plus B times C over B times D. That's just getting a common denominator. But this in turn will be A times D plus B times C over B times D. So what do you think about that? Well, since the set of integers is closed under addition and multiplication, and B times D is not equal to 0 by the zero product property. What can we say? R plus S is rational. And that's by good. It's by definition of rational numbers. And we're all done with that proof. Isn't this fun? Okay. It says a lot about me that I'm so excited that we're dealing with characters, mathematical characters again. All right. So now, a lot of times what we're going to do is, definitions are great. You know, using definitions for proofs, they're very solid. You're allowed to use them. You know, they're just like kind of gospel, right? But you can also use previously proven theorems, right? So if we take a look at this corollary to that theorem that we just proved, it says that the double of a rational number is rational. So, okay. I mean, if I wanted to put this in an if-then statement, what would I write? Well, we could say if a number is rational, then twice that number is rational. All right, well, let's check it out. We're going to be using, a lot of times, by the way, people shorten proof to PF, right? So we're going to be using the theorem from before. So why don't we say let R be, you could just say let R be rational. I notice your author, you know, emphasizing let R be any rational number or whatever she's naming things. She's careful that it can be any number from that set. Well, what is doubling something? It's adding that number to itself twice, right? So 2 times R is equal to R plus R, right? Well, therefore, 2R is rational because that last theorem we just showed in theorem 4.2.2 that the sum of any two rational numbers is rational. So a number added to itself is also rational. So we'll just say this is by theorem 4.2.2. All right? And we're all done. Cool, cool, cool? All right, so here, let's consider this statement, all right? The cube of any rational number is rational, right? And let's go ahead and, prove this using definitions of using the definition of rational numbers. So let's officially restate this. Okay, so you've learned a few ways to restate this. The cube of any rational number is rational. So one way you could do this is for any rational number its cube is rational. Well, that's all good, but it's not really our if-then statement, right? So if a number is rational, then its cube is rational. So we know our premise and we know our conclusion. Working with that premise, do you think it's true? Well, think about it. Isn't 1/2 a rational number? And 1/2 cubed is 1/8, which is also rational. I think it's going to work, right? So I think it's true. Here was our restating. And now let's do our proof. So, well, we need to have a rational number, right? So why don't we let R be any rational number Well, if that's true, there exists an A and B that belong to the set of integers, right? Where B is not equal to 0, such that R is equal to A over B. Cool so far? Awesome. So, all right, what do we need to do now? We have our R equals A over B. Well, what is R cubed? R cubed is equal to R times R times R. It's repeated multiplication. So this is going to be A over B times A over B times A over B. And that would be by substitution. So this is A times A times A over B times B times B, which is rational since the set of integers is closed under multiplication. So remember, when you multiply two integers, you get an integer out. And we're all done. Cool, cool? All right. So notice one thing. Notice that when we were trying to decide if it was true, we did kind of mentally work it out an example. And you could have even written it down on your paper. But we didn't use specific integer values in order to complete our proof. I mean, this A and B that we put in there could take on any integer value with the exception that B couldn't be 0. All right. So that is definitely one of the tricks for proofs. All right. So example 3, part 1. So these kind of all go together. If R and S are any two rational numbers, then R plus S, that quantity divided by 2, is rational. So this is already in our if-then statement. So we're ready to go. All right, so proof. What do you think we should do? Well, why don't we go ahead just to be on the safe side and let R and S be rational numbers, as our premise states. Well, since they're rational numbers, there's got to exist integers A, B, C, and D, because we have two rational numbers, with B not equal to 0 and D not equal to 0, such that R equals A over B and S equals C over D. All right, well, let's go and do some fun math. So we've got R plus S divided by 2. Well, by substitution, what will that be? Beautiful. R was equal to A over B, and S was equal to C over D. So all I'm doing is N for R, I'm putting my A over B, and N for S, I'm putting the C over D. And again, this is going to be by substitution. Don't worry, I didn't forget about the 2. And then all of this will be over 2. Well, what can we do with that? Remember that we did a problem kind of like this. Didn't we end up getting AD over B times D plus BC over B times D, just by getting a common denominator, all over 2. Go ahead and move the equal sign down a bit. And then this is just going to be AD plus BC over BD all over 2. But what is that? That's going to be AD plus BC all over 2 times B times D. All right, well, what do you think? Since the set of integers is closed under addition and multiplication, and 2, which is an integer, times B times D is not equal to 0 by the zero product property, then R plus S over 2 is rational. Awesome, wasn't that fun? Okay, so notice how much stuff I'm writing down. Yes, you need to write it down, because oftentimes the hardest proofs, like when I teach linear algebra and they're proving properties for vectors or for matrices, the proofs are just those basic properties, because they assume things about vectors because they're similar to what's happening with the real numbers. But you have to get things down to their components, their vector components, in order to apply properties for real numbers. So sometimes it seems very obvious and clear, but it's always better to put why things work. Okay? All right, so here we go. Now on this one, I took a little a screenshot. I gave you very small pictures of this in the 4.1 video. These are theorems about inequalities that we can use for this particular proof that you might not have necessarily remembered. So here we go. For all real numbers a and b, if a is less than b, then a is less than quantity a plus b over 2, which is less than b. So for this proof, what do you think we should do? Well, why don't we suppose that A and B are distinct. We want to say distinct real numbers because of that inequality. Now, since A is less than B, if you look here in these theorems, if you add the same quantity to both sides of an inequality, the inequality holds true, right? Even if you add a negative. So here what we could say is we're going to do this twice, all right? And so we're basically going to work with one side of the inequality and then the other side of the inequality, right? So if we work on this left side first, isn't it true that if I add A to both sides by this theorem, which I think was theorem 19, right? T19, that is true. But how many A's do I have? I have 2 A's, and that's less than, I can commute those because the real numbers are commutative. And I get 2 A's is less than A plus B. So now I have this 2 times A is less than A plus B. Well, let's say that I multiplied both of these by 1/2. And 1/2, do you agree, is greater than 0? So no worries about the inequality, right? So this actually will fall under that theorem 20, right? I multiplied both sides by a non-zero real number. And so the inequality holds. And I'm sorry, not just non-zero, but greater than 0. So put that aside for now. Similarly, if I work on the other side, A less than B is equivalent to A plus B less than B plus B. And remember, that was from theorem 19 again. Well, looking at this, do you see I would get A plus B is less than 2 B's? And applying the same idea as we did previously, we would have A plus B over 2 is less than B. And so for that one line, we ended up using theorem 20. So for our conclusion, all we do then is we put those two inequalities together. We had up here that A was less than A plus B over 2. And then over here we have that B is greater than A plus B over 2. And so therefore, A must be less than A plus B over 2, which in turn is less than B. And we're done. That's what we needed to show. All right? Cool, cool? Alrighty, so the third part here, we're going to actually utilize the first two parts of what we just solved, of this example. So, given any two rational numbers r and s, with r less than s, there is another rational number between r and s. Okay, well again, let's suppose r and s are two distinct rational numbers. And why don't we let t equal to r plus s divided by 2? Therefore, by the results of example 3, parts 1 and 2, t is rational and r is less than t is less than s. And that's what we needed to show, right? If you want, you can restate it in words. You could say, therefore, there exists a rational number between r and s. Cool, cool? All right. So here we come to our last proof, which is another kind of groovy one. If a real number c satisfies a polynomial equation of the form r3x cubed plus r2x squared plus r1x plus r0, where r0, r1, r2, and r3 are rational numbers, then c satisfies an equation of the form n3x cubed plus n2x squared plus n1x plus n0 equal to 0, where n0, n1, n2, and n3 are integers, right? So when you're dealing, with taking something from a rational representation to an integer representation, you want to throw in some integers. Well, so we don't have to go super far into the alphabet. Let's go ahead and set it up where we use subscripts on our integer representations as well. So there's a couple of different ways one can do this. You're going to see in proofs where we don't know what n is, n being, or when we don't ever really know the subscript, how high the subscript of our coefficient goes and the power on our variable goes, we often will, denote it in a cleaner way. So I'm gonna kind of show you a couple of tricks here that you'll often see used. All right. So let's start this out by getting our tools ready. All right. And just one thing, if c satisfies the, we'll say A, polynomial equation of the form r3x cubed plus r2x squared plus r1x plus r0 equal to 0, then it follows that, well, if you've got something that satisfies an equation, it means that that something can go in for x. So you would have r3 times c cubed plus r2 times c squared plus r1 times c plus r0 would equal to 0. And that would just be by substitution. So let's see what else we need to do. Let's go ahead and establish what our r's are. Okay. Now I'm not going to use any n's here because we're going to use n's at the end to represent our integers. So let's say this. Why don't we say since r sub k, where k equals 0, 1, 2, and 3 are rational, there exists an AK over BK, again, K equal to 0, 1, 2, and 3, such that RK equals AK over BK. And AK and BK are integers with none of these BKs equal to, none of them can be 0. Okay? All right, so we have our setup going on. Now, all right, coming from that equation where we substituted in the C, we have r3c cubed plus r2c squared plus r1c plus r0 was equal to 0. Now, if we substitute in the a over b, the proper subscript for the r's, we would have what? Beautiful. We would have a3 over b3 times c cubed plus a2 over b2 times c squared plus a1 over b1 c plus a0 over b0 equals 0. And that again is just by substitution. And okay, well, what do you think we ought to do? How could I clear out the denominators? I mean, if I multiplied both sides of the equation by b0, b1, b2, b3, b0, b1, b2, b3, let's see what I would have. Well, and remember, it distributes. This is going to distribute to each term on the left side. And so each time one of the factors of b will divide out. So in the first case, it's what? Perfect. It's going to be the b3 that would divide out. So we would have a3 times b0, b1, b2, and then that would be times our c cubed. Plus, what would we have? Perfect. We would have a2 times b0, b1, b3, plus a1, whoops, sorry, in my c here, that would all be times c squared, plus a1 times b0, b2, b3, and this would be times c, and then plus a0 times b1, b2, b3, and that's going to equal to 0. So each of the quantities that are in the parentheses are going to be what kind of number? Beautiful. Integers, because when you multiply integers together, you get integers out, right? So if we let n3 equal to a3, b0, b1, b2, n2 equal to a2, b0, b1, b3, n1 equal to a1, b0, b2, b3, and then n0 equal to a0, b1, b2, b3. Okay, so the ni's, I equals 0, 1, 2, and 3, are all integers by closure. So we have n3c cubed plus n2c squared plus n1c plus n0 equal to 0. And that's what we needed to show. All right, well, my dogs are barking. Haha. It's time to get going. If you like what I'm doing, please subscribe and let me know what else you need. And I hope that you enjoyed this show. Have a wonderful morning, afternoon, or evening. I'll talk to you soon. Bye.